Hi everybody. I'm going to talk about LU decomposition. And as I mentioned in the last video, this is kind of a substitution for the matrix inverse. Right? You can solve systems of linear equations or matrix equations using matrix inverses, but actually a somewhat better way to do it, more efficient computationally, is to use just Gaussian elimination if you only have to solve for a single system or a single matrix equation, or if you have to solve for a whole family of related matrix equations using the same matrix A, same matrix of coefficients A, then you can use LU decomposition in place of the matrix inverse. So let me talk about this. I'm actually just going to work through an example that we did earlier. So I think this is the first example I did in chapter 6. I did the example where A was a 3 by 3 matrix, 2, -2, -3, 1, right? This guy over here, and B was -1, -1, 5, and we were solving this system. And we did it, actually, when I did it originally, I set it up as an augmented matrix, so we had these numbers on the left and these numbers on the right combined into a single matrix. Now I'm going to keep them separate in this, in reviewing that example. And remember that we worked out the multipliers, so the ratio of 3 to 2 is the multiplier M21, and the ratio 4 to 2 is the multiplier M31. After finishing the row reduction and finishing the first column, we then moved on to the second column, and we figured out that the multiplier M32, at that point, the ratio of the third entry to the second entry was 11 halves. No, I'm sorry, it was 10 halves, right? Wrong. No, it was 10 over 11, that's it, 10 over 11. After transforming the matrix by fixing the first column, now the ratio of the third entry to the second entry was 10 11s, M32. Okay, now, and then having done that much of the row reduction, we ended up with what was an upper triangular matrix, right? The matrix A had been transformed into this, where we had zeros in the lower left side of the matrix, right? So the lower left part of the matrix was all zeros, and that's what we mean by an upper triangular matrix, that the lower left is all zeros. May sound like a trivia question, but suppose we're given U and the multipliers Mij. Is there a way we can recover the original matrix A, right? That seems like it ought to be simple to do, and it is. The multipliers were the numbers we used when we were subtracting off multiples of rows to simplify the lower rows, right? So for example, this multiplier here, M21, we use that to multiply by the first row and subtract that multiple from the second row. So we modified the second row by subtracting M21 times the first row. So it seems like we ought to be able to recover the original second row by adding that number back, right? So it seems that we ought to be able to take the second row, this is the second row from the upper triangular matrix, and recover the original second row by adding back in M21 times R1. Of course, the first row of the upper triangular matrix U is the same as it was in A. That's absolutely the same. So R1, the original R1 is the same as the R1 at row 1 in the reduced matrix, in the upper triangular matrix. To recover the third row of A, we just have to basically do this recovery operation twice. We start with the current R3, which is the result of subtracting two multiples of 2 rows from the original A, right? We subtracted a multiple of the first row to get this 0, and then we subtracted a multiple of the second row to get this 0, and we just add them back in. So we add back in the multiple of R1 and the multiple of R2 that we used. And now you can perform all 3 of these recovery steps simply by matrix multiplication. By multiplying the U matrix over here times this matrix on the left, we're going to perform all these recovery steps, right? So for example, if we multiply, when we multiply the first row over here, 1, 0, 0, times this matrix, this says take 0 times the third row plus 0 times the second row plus 1 times the first row. In other words, we just copy the first row from U, right? And so the original R1 is the same as the R1 in U. No change is required. When we multiply the second row over here times U, we get 0 times the third row, 1 times the second row, so we copy the second row, and then we add in M2 1 times the first row. And that's exactly what we said to do here. Take the row R2 from the reduced matrix U and add back in the multiple that we had subtracted earlier, right? And then again, the third row says that, the third row of this matrix says we should copy the third row of U and add in M3 2 times the second row plus M3 1 times the first row. So what we get, what we get is this interesting pattern where we've got a lower triangular matrix in the sense that the only non-zero entries are in the lower triangular side, at or below the main diagonal, times an upper triangular matrix, right? And because the only non-zero entries are on or above the main diagonal. And when we multiply those two together, we recover the original matrix A. So this is called the LU factorization of A, because we factored A into a lower triangular matrix times an upper triangular matrix. Okay, so having solved for G, we can now recall that by definition, G was equal to U times X. So, knowing what G is, now we can solve for X. So plugging everything in here, we're solving this problem. But notice that solving for X at this point is equivalent to doing back substitution, right? It's equivalent to being at the stage we were at after doing the row reduction, and then just having to use back substitution to figure out what the X values were. So we start at the bottom. The last row, let me try that again. Oops, the last row of this matrix equation says that 0x1 plus 0x2 plus 24/11 x3 equals negative 24/11. So we divide negative 24/11 by 24/11, and we easily figure out that x3 equals negative 1. In a similar way, the second row of this matrix equation says that 0x1 plus 11 halves x2 minus 7 halves x3 equals 7 halves. So we can easily solve for x2 by taking 7 halves, subtracting off this term, which represents negative 7 halves times x3, x3, which we know is negative 1, and then we divide by the coefficient of x2, which is 11 halves. Now in this case, the numerator is 0, so this just turns out to be 0, so x2 is equal to 0. And then the the first row of the matrix equation says that 2x1 minus 3x2 plus 1x3 equals 1. So again, we solve by starting with the 1 here, subtracting off this term, which is 1 times x3, 1 times negative 1, subtracting off this term, negative 3 times 0, and then dividing by the coefficient 2, and we end up with 1. So x1 turns out to be equal to 1 over here. Therefore, we've got our solution now. X is equal to 1, 0, negative 1, right? The 1 is at the top and the negative 1 is at the bottom, right? Okay, so we solved for X, and that was not difficult to do at all, right? It was a very straightforward process of solving for one variable at a time, plugging it back in to solve for the next variable, right? This was maybe just slightly harder, just marginally harder than doing the previous stage, right? Doing this stage, we didn't have to divide by anything because the coefficients on the diagonal were all 1, so we didn't have to do any division. This was actually slightly easier. It was a very similar process, notice, right? That we, except that we started at the top with x1 and we worked down to x2 and then to x3. But very similar process. We work out a variable, plug it into the next equation, and solve for the following variable. This is called forward substitution because we work in the forward direction, and This is called back substitution because we work backwards from x3 to x2 to x1. Forward substitution is slightly easier because you don't have to divide by anything, right? Not a big deal though. Okay, so to summarize, if you want to solve an equation ax equals b, and you know the factorization, A factors into a lower triangular matrix L with ones along the diagonal, main diagonal, times an upper triangular matrix U, then you can very easily get the solution for x by following a two-stage process. We solve for g in the equation L times g equals A, right? So we're saying that g is equal to u times x, and therefore we solve for g by saying LG equals A, right? And we solve that by forward substitution. Then, having figured out what g is, we solve for x in ux equals g, and this is easily done using back substitution, right? So if we know what L and U are, we can easily get the solution without much work. Finally, let me comment on how you do this in MATLAB. In MATLAB, there's a built-in function, LU function, and you give it a matrix, right? And it will automatically produce a decomposition of A into L times U. Sometimes it requires pivoting. Now, the example I did earlier, I didn't do any pivoting. But in general, recall that sometimes it's necessary to pivot when you do row reduction. So the LU function in MATLAB will also take that into account. So it returns three elements. It returns a lower triangular matrix L, an upper triangular matrix U, and a permutation matrix, which I'm calling P here, that represents the ways the rows had to be rearranged during the pivoting of the matrix. So the way you use it in practice is, well, L is the lower triangle, U is the upper triangular, P is the permutation matrix, which has the pivoting information. So what this means is if you want to solve an equation like AX equals B, what you do is you replace B with the permuted form of B. You multiply P by B, and then you can so in other words, that performs all the pivoting necessary on the B matrix, and then you can solve, as we discussed before, you can solve L times U times X equals B times B, first doing a forward substitution to figure out what UX is, and then once you've got UX, you do backward substitution to figure out what X is. Okay? By the way, permutation matrix looks kind of like this. It's like an identity matrix where the rows have been permuted. They're in different orders. So, like for example, this permutation matrix, if you multiply it times a vector on its right, it would have the effect of simply reversing the first and second entries, right? It just reverses row 1 and row 2. So that's what a permutation matrix looks like. Just an identity matrix that's been with scrambled rows, and it just changes the order of the entries in the vector you multiply it by. Okay, now let me turn to MATLAB. Okay, so now let's try out that last example that we did on MATLAB. Recall that you can enter a matrix using semicolons to indicate where the lines end. So this would be how you enter our A matrix, right? And let me see, what was our B matrix? For the last example, B was this guy, right? B was 1, 5, 3. Okay, so now you can use the LU command to decompose A into L times U with a possible permutation matrix P. So let's see, so I'll say LU P equals LU of A. Okay, so it gives us the lower triangular matrix L, upper triangular matrix U. Oh, it did actually permute them. Now, actually, I overlooked this when I was talking about this, but if you look at the first column here, 2, 3, and 4, if we had done pivoting, we would have pivoted the first row with the fourth row, right? because the fourth row has the bigger entry in the first column. So if I'd been interested in pivoting, that's what I would have done. I would have pivoted the third row with the second row. So that's what this represents. It says that we replace the, let's see, what does this mean? This means that the first row got switched to the third row, and the second and third rows got switched maybe at a later stage. So anyway, there would have been pivoting if I'd been paying attention to that, but I wasn't. Okay, so now recall that we have to take into account the pivot when we solve the matrix equation. So effectively now we're going to be solving LU times X equals PB, right, rather than just B. So first step is we define G. G is going to be equal to the solution when we solve for solve the equation L times G equals PB. Now, there's another shortcut you can use in MATLAB to do this. In a sense, when you solve L times G equals something, in a sense, you want to divide out the L. We never talk about division when we're talking about matrix operations, but that is, in a sense, what we want to do. And so MATLAB uses that as a shorthand convention. We say L divided into, notice that's a backslash. It's like we're dividing on the left by L. Of course, in matrix operations, you'd have to distinguish between dividing on the left or dividing on the right. Here, we specifically want to divide on the left by L, and we want to divide the matrix P times B, right? We have to permute B according to the pivoting that was done in doing the row reduction. Okay, so we do that, and there's our G value. Okay, 3, negative 1/2, 2.4. Having done that, now we can use the same kind of shorthand to figure out X. X would be equal to, now remember, X is the solution of U times X equals G. So again, we kind of want to left divide the G vector by the U vector. So use that shorthand again. U left divided into G that we just figured out, and there's our solution for X. So it worked. One final note, I want to reassure you that when you use the MATLAB backslash operator to solve these linear equations, MATLAB is smart enough to carry out the computation in the optimal way. So for example, when you're solving G equals L backslash P times B, right, where you're trying to kind of left divide by this lower triangular matrix L, MATLAB is smart enough to know that when you're dividing out a lower triangular matrix, that the optimal method is to use forward substitution. So it will do that optimally. And similarly, when you're solving for X, X equals U backslash G, in this case, U is an upper triangular matrix. MATLAB is smart enough to know that the optimal way to do that is to use back substitution. Right, so you don't have to worry about that. MATLAB is smart enough to do that optimally. Right, MATLAB is smart. There we go.